I will put my presentation.
Yes, it's visible. Kindly start your presentation.
Okay.
We can't see you though, but your presentation is visible. Please start.
Okay. Yes.
Thank you.
My name is Leonardo Cano. I'm from Argentina, from Research Institute of Materials, and we talk about the development of new nanocomposite for the remediation of contaminated water. Next, please. I think that you miss one diapo. Please go back. Please go back in the presentation. I think that the presentation means no. Maybe I can share my screen with the presentation.
You can share your screen.
Yeah.
Or is it
yeah,
okay?
Please. Yeah. Okay. Please. You see it?
Yes. Kindly
Okay.
start.
Yeah. Then I want to talk about the development of new nanocomposites for the remediation of contaminated water. I'm from Argentina. I'm from INTEMA, the Institute of Research in Science and Materials Technology. Here in this institute, we work in different kind of materials like polymers. We have work in corrosion, in welding and fractometry techniques, and metallurgy, catalysis, and ceramics, for mention someone of that. In our group, we developed thermoplastic composites. And this is a picture of our lab. And we developed different materials of composites, like biocomposites for containers and packaging, composites materials with high mechanical performance, modified clays as reinforced of polymeric materials, and hydrogels with applications in biomedicine and agro and water treatment. This is the last one. Is the time is the highlight of this presentations. Yeah, and now hydrogels. What are hydrogels? Well, hydrogels are composed of polymers that form three-dimensional porous structures. They are capable of swelling in water without dissolving or losing its shape. There are soft material with good mechanical properties, and it's possible to incorporate in organic reinforcements and easily removable from the treatment medium, which is one point very, very interesting for the applications in treatment of waters. In our group, we work with 4 different polymers which form hydrogels. There are polyvinyl alcohol, polyacrylic acid, chitosan, and sodium meshinate. Downtown, I'm going to present 2 results, 2 research apply research with a removal of some contaminants. In this first part, I will talk about a nanocomposite of layer double hydroxides with biopolymers with potential applications in nitrogen removal. What are those laminar double hydroxides? There is a positive charged metal hydroxide sheets that are stabilized with interlayer anions, also called anionic clays because your charge is negative. And between these laminar double hydroxides, you found the hydroxide that is a hydroxide of magnesium and aluminum. There is many uses of these compounds. I will maybe frame rather than energy storage, catalysis, control release, and contaminant absorption. The structure of these laminar double hydroxides is like this, and you can see a laminar composition with magnesium and aluminum, and interlaminar composition with different anions. In my lab, you can synthesize these compounds. These compounds exist in nature, but you can synthesize in lab, and you can control these properties between the control of the synthesis parameters. In this case, we utilize a co-precipitation method with 3 solutions, one from magnesium and aluminum, one for hydroxides, and one for carbonates. You can see here the results of this synthesis is the XRD and the adsorption of nitrogen. You can see in the XRD that the sample shows the typical peaks for the planes of layer double hydroxides that identify that you obtain in this synthesis the compounds required. And in the graph of absorption of nitrogen, you can see that a structure, the porous structure of these compounds, that you see that external surface of 111 meter quadrats per gram, and volume of total pores of 4717 cubics per gram. This result is very good and is comparable with the bibliography. Then, when you synthesize the compounds of L8H, the hydroxide, we incorporate the compounds in these different matrices of polymers, like PBA and alginate. You can form beads of PBA and alginate, and you can incorporate in this bead the layer double hydroxide. These from compounds that seems like in the photography. You can see the compounds with PBA, alginate, and layer double hydroxides. These beads are the hydrogels. Yeah, and you can see scanning electron microscopy of these beads with different post-treatments. Here, post-treatment is only dry in an oven. This is lyophilized, and this is submitted to freezing Taiwan sequence. You can see that the lyophilized particles have more huge pores. That is very important for the application of adsorbent contaminants. In all cases, the crystal of layer double hydroxide are distributed homogeneously in other polymers. when you test this type of compost for the removal of nitrates, you can see that you reach 40% of remotion in a short time, maybe 2 or 3 hours. This is about the impact for this. And then you can elaborate at different hydroshels, but now with another clay that is bentonite. It's a natural clay from Argentina, and use it for remediate the arsenic. The contamination with arsenic is very, very important here in Argentina. These are the beads in the front, and in the front you can see the bentonite, the clay. Yeah, bentonite. Bentonite is a clay composed essentialmente of minerals from S-type group. In the Neuquén, Basin Neuquén is a region in Argentina, is rich in mammaryllionite. Mammaryllionite is very, very known for others investigation. And you can see the XRD that confirm the structure of mammaryllionite. And you can see again the results of absorption of nitrogen. And you see a standard sulfides of 61 meter quadrats per gram and a total volume per of 0.11 centimeter cube per gram. These results are and agree with the literature and confirms that we have the structure of mammaryllionite principle. Again, we incorporate this bentonite in a matrix of polymers like PBA and HLH.
And we form little bits of PBA, HLH, and bentonite. You can see now the different bits when in the micrography, and you can see clearly that the pores of the bits previously to incorporate the bentonite is such bigger, and this is a little reduction. And here you can see the uniform distributed bentonite in all the composite. Then we're going to the result of arsenic removal with these beads, and you can see that we have a 100% of remove at 24 hours of treatment. What is a huge removal and very important results for us. It's possible to remove 100% of arsenic, and after of 6 hours of treatment, a removal of almost 17% of is achieved. It's a very good result for very short times. Now, conclusions and perspective. We can obtain beads or different polymers containing different reinforcements, such as layer of double hydroxides and bentonate. The obtained beads present a robust and very porous structure with a good dispersion of the nano-enforcement. The liophilicid beads show a much higher grade of swelling than the others, and indicate that post-treatment is useful in a potential product for the removal of contaminants. And the beads proved to be active to the removal of nitrates and arsenic from the water. The removal of contaminants will be evaluated in a continuous method like a treating column. And in the future, other polymeric matrices like such as chitosan and another clays reinforcement like carbon will be tested. Thanks, and this is an image of my city, Mar del Plata.